My name's Tom Honeyands. I've been in the industry for around 35 years now. In the last 10 years I've been here at the University of Newcastle leading the research centre. Steel's a really important sector to decarbonise, and we know that over the next decades we're going to need more steel as we move to a zero carbon or a net zero carbon economy. But at the same time, steel's a very big emitter of CO2, so we really need to work hard to decrease the emission. And really there's not going to be one single solution to decarbonising the iron and steel industry. The solution applied is going to depend on a number of factors, such as the availability of scrap, the availability of renewable hydrogen or natural gas, the local iron ore supply, and then the grades of steel that people are trying to make as well. For the next few decades, the steel will still be produced using the blast furnace. So one of the really important things is to reduce the emissions of these blast furnaces and look at how Australian iron ores and Australian coking coals would behave in a low emission blast furnace with hydrogen. So to replace the blast furnace, the increasing use of scrap is really the easiest abatement lever. So people are looking at that, particularly in places like North America where there's lots of scrap available. There's also some issues with use of increased scrap. So you can't make every grade of steel that you want to make from a scrap melting electric arc furnace. Over time, residual elements like copper and tin build up in the scrap supply and would negatively impact steel quality. To address this, people are looking at direct reduced iron or DRI as an alternative to scrap, or to augment the scrap and then melt that in an electric arc furnace. So one of the first technologies to talk about is the DRI EAF, so direct reduced iron electric arc furnace process route. A really good example of this is HYBRIT. So in Sweden they have high grade pellets, renewable electricity from hydroelectricity, and a steel market that's quite willing to pay a premium for green steel. So for the DRI EAF process, like HYBRIT, you're really starting with very high grade iron ore pellets. So typically this means taking an iron ore, like a magnetite iron ore, grinding it up very fine, so less than 100 microns, doing some beneficiation, typically magnetic beneficiation, which upgrades the iron ore to around 67%. It can then be fired and made into pellets, which can then be fed into the direct reduction plant. So ZESTY is a really interesting local innovation that we can take finely ground iron ore and react it with hydrogen in an electrically heated tube and make DRI. Some of the really interesting things about it are the fact that it's electrically heated already, so you're not trying to replace coal or some natural gas firing. You can use renewable electricity if it's available to heat the reactor. Another really good thing about it is you're not dealing with very thick refractories that have to be kept hot all the time. So it does open the possibility for intermittent operation. It would be quite challenging to scale up to the same level to replace a blast furnace, say, but you could certainly make enough steel to augment scrap in an electric arc furnace and improve the quality of the steel made from that process. The direct electrolysis of iron is another really exciting new development that people are working on quite hard at the moment. In the direct reduction process, we're using electricity or electrolysis to make hydrogen from water, and then using the hydrogen to reduce the iron and then melting the iron later. So what the direct electrolysis leaves out all those middle steps and uses the renewable electricity directly to try and make iron from the iron ore. One of the first examples of this is the molten oxide electrolysis, which has been pioneered by Boston Metals. The gangue elements, the silica and the alumina that are present in the iron ore, would actually become part of the molten oxide at the high temperature. So you could think of this like an aluminium reduction cell, where you have an anode and a cathode and an electrolyte that's operating over 1600 degrees. So if you could scale this up and get it to work at a commercial level, then that would be fantastic, and that you could use renewable electricity directly on the iron oxide. But you can imagine that at 1600 degrees, the materials of construction are quite challenging. So at the University of Newcastle, we're also working on an electrolysis process. So this process would dissolve iron oxide or iron ore in a molten salt and use, again, renewable electricity to try and make a solid iron product at an intermediate temperature of around 700 or 800 degrees. And we think this has good advantages potentially compared to the electrosteel at low temperature and the Boston Metals molten oxide electrolysis at 1600 degrees. In the end, all of these technologies we've been talking about will have a role to play in decarbonising the iron and steel industry. So it's a huge challenge. At the moment, the iron and steel industry is around 7% of global CO2 emissions, and obviously it has to be brought down, and not one single solution will be able to solve all of the problems. So depending where you are in the world, what your iron ore source is, what the steel products you're trying to make are, and the type of renewable electricity you've got available, I think each of the technologies would have a role to play, and combining all of them should get us close to the net zero by 2050.